Okay, so let's talk about the kinetic and molecular theory of matter. So, kinetic molecular theory, also abbreviated as KMT, explains the constant motion of gas particles and models ideal gases, also known as perfect gases. Now, there are 6 main points of KMT. And the first one is gases consist of many tiny particles that are far apart relative to their size. The second point is the idea of pressure. Now, pressure is a measure of the force that the gas exerts on the walls of its container. So pretty much collisions. So when we're recording pressure of something, we're recording the number of collisions going on. So with that idea, collisions are elastic, meaning there's no change in kinetic energy. Kinetic energy is the energy of motion. So given that collisions are elastic, they're just jumping right off of each other and continuing on their regular speed they were doing before. So always having that kinetic energy, as it says, it's always in motion. So when the number of collisions go up, we know the pressure goes up. And the number of collisions go down, we know the pressure is going to go down. The third point is gas particles are always in motion, so they always have kinetic energy. I kind of talked about that before. They are never going to become standstill. If the particles stop moving, it's no longer a gas. And point number 4 is there's no force of attractions between the particles. Particles in the gaseous form do not want to bond with their other particles. So if you ever play with a magnet and you try to put 2 magnets together and with all your might they just don't want to connect, you feel that kind of force kind of removing them from each other. That's kind of like how gas particles are. They kind of try to want to stay as far away from each other as possible and they repel each other. So that's why if they do collide, it's an elastic, they just jump right off. Now, number 5 talks about temperature. Now, when you think about the definition of temperature, you would think temperature is how hot or how cold something is. Well, that's actually incorrect. Temperature is the measure of the average kinetic energy of the particles, so motion. So if we're recording temperature of something, we're recording how fast or how slow the particles are moving. When you're sick, we all know that we get a fever, so our temperature increases in our body. That's because our cells, our particles in our body are moving faster to kill off any bacteria, virus, or whatever is making us sick. Okay, so with that idea, the faster the particles, the temperature's higher, so there's a higher kinetic energy. And when there's slower particles, the temperature's lower, so there's a lower kinetic energy. And lastly, this does not apply to real gases, so real world gases, because we know the real world is not a perfect world. There's different things that can change different things. This does not mean that temperature is not motion and collisions and pressure is not collisions. It just means we can't be 100% that these theories happen on real life gases. But we do have software, we do have machineries that we can make perfect conditions to test out these points, which is how we got them. Okay, so let's talk about boiling point. Now, a lot of you guys might think that boiling point is the temperature at which something boils. That is actually incorrect. The boiling point is when the vapor pressure equals the atmospheric pressure, so the pressure of the atmosphere. So when the pressure of the atmosphere equals the vapor pressure, that is when something boils. Now, with the boiling point, you actually don't always need heat to reach the boiling point of something. Meaning, you don't necessarily need to put in fire, put in any heat to boil something, because boiling point's based on pressure. Now, what is vapor pressure? Well, vapor pressure is the vaporized particles colliding with the walls of the container. And usually this happens at the surface. So once we start kind of having that transition between a liquid to a gas, those gas particles, those vaporized particles on the surface, are going to start colliding to the walls of the container. For instance, boiling water, they're going to start colliding on the walls of the pot, and that creates that vapor pressure on the surface. So that surface vapor pressure needs to equal the atmospheric pressure, so the pressure of the atmosphere, for it to officially boil. And again, this is all dependent on pressure. So kind of thinking about altitude wise, okay? So I bet in the summertime, when you guys go to the swimming pool and you go dive straight down to the bottom, your ears start to pop. That's because pressure, the atmospheric pressure, increases as we go down in altitude. So if that atmospheric pressure is increasing, that's going to result in, again, an increased atmospheric pressure, resulting to an increase of boiling point. And oppositely, if we're increasing our altitude, let's say we're climbing up Mount Everest, the atmospheric pressure actually decreases. And we know this because you guys all know about Mount Everest, one of the tallest, the highest summits in the world. Now, a lot of people, when they do go on the hike up to the summit, they do die because of altitude poisoning, also known as oxygen poisoning. Because if the pressure is low, that's less particles. Oxygen particles are not colliding to you as fast. So that's why it takes a long time to climb up to the summit, because you have to sit in base camp to get your body acclimated, used to the lack of oxygen as we go up. So when altitude increases, the atmospheric pressure decreases, which results to a decrease in boiling point. So summary, altitude decrease, atmospheric pressure increases, boiling point increases. And as altitude increases, atmospheric pressure decreases, causing a boiling point to decrease. So this pretty much says that people in Colorado, that live in Colorado, for instance, of course it's in the mountains, it's higher altitude than where we live, can boil water a lot faster than we can, because they have to reach a lesser pressure than we do to boil water. So now let's actually look at some demos. First, you're going to go ahead and see me actually boiling water without any heat. And then we're going to see, okay, how do I know vapor pressure is a thing? How do we know there's vaporized particles on top of the surface of a liquid?
So we just talked about boiling point, and boiling point is when the atmospheric pressure equals to the vapor pressure, so what's being emitted from our liquid. Now, we also talked about that we don't need heat. We don't need a change of temperature for something to boil. So right now I have a beaker of water, just regular old room temperature water in this. I call this the Willy Wonka machine because it sounds like the little train in the Willy Wonka and the Chocolate Factory. But this is a vacuum. So what it is, it's increasing massive pressure inside here. And as you can start seeing, it starts bubbles a little bit on here. It's kind of like that simmer when you have water. And soon it's going to get into a roaring bubble. Now, there's no temperature change in here. I am not putting any heat in here. So when I end this, it's going to still be room temperature inside here. So we'll let this see some little bubbles and stuff on here starting to form. All I'm doing is I'm changing the pressure. It's the same idea for pressure cooker. Pressure cookers, no heat at all. What's happening is that the pressure in the pressure cooker is increasing, and that's causing whatever the food is to heat up. It's a different word, not the same heat energy we use in science. It's more, just a different definition for that word. As you can see, we've got a lot of bubbles, and it's starting to bubble a little bit. Let's see, a little bit more. I hope you guys can see those bubbles in there. Here, I can bring it closer. As you can see, we got some bubbles on there. Now, this machine does not work perfect, but as you can see, it starts bubbles right now. We're going to call that boiling. This machine's very old, so the vacuum isn't as perfect. Oh, but we're getting a lot of boiling. There it goes. It's kind of boiling right there. Alrighty, so now I'm going to remove. I'm going to turn off the vacuum. I'm going to release the pressure inside it. And when you guys are boiling water for like cooking ramen or mac and cheese, heating noodles, the pot's very hot. So probably you guys are thinking, are very suspicious right now what's going on. There has to be heat, there has to be temperature. Well, you can't grab the pot, right, when it's pasta, because you know you're actually putting heat into it. Well, grabbing this, not burning. It's actually very cold. It's actually completely room temperature. Kind of a little bit cold. It's kind of cold in this classroom. So there you go. We were talking about vapor pressure, and we know that vapor pressure is the pressure when a liquid becomes into a gas, and what that gas is when it collides off the walls, it's producing some pressure. So let's prove that pressure actually exists. So I have this water canister of sorts, has rocks in it for some reason. And I'm going to put some alcohol. It's ethyl alcohol here. No, it's not the alcohol we drink. This is different types of alcohol. And we are going to put that into the bottle. That should be perfect. Then I'm going to seal the top with some parafilm wax. This is pretty much wax. It's easily mendable to cover up any areas to prevent any air to get into. I'm going to just agitate it, and what I'm doing right now is I'm increasing the liquid to become a gas. I'm waiting for it to vaporize. You start seeing the bulge on top. Already you can see some kind of pressure, some kind of gas forming. Sorry guys, that's my phone. Alrighty, we get a nice. And I also want you guys to observe how much liquid we have right now, and we're going to compare that what we're going to have later as well. Alrighty. Let me go ahead and get some tongs, turn off the lights. And let me get my matches. Should be right here. Alrighty. Now, let's watch the magic happen. There we go. Alrighty, so let's let that cool down a little bit. So what just happened was I lit the gas, and obviously the fire happened. And if you notice on the bottom, we have a lot more liquid than what we started with. Because remember when we talked about types of reactions? This was a combustion reaction. The alcohol was our organic compound. It reacted with the air, the O2 in the air, and it produced that carbon dioxide, that gas, and the smoke, and a little bit of water in here. So it's obviously it's not pure water. I can't drink this, but it's we have a lot more liquid than what we started with. Alrighty, thanks guys.
Okay, so now at the very end of this, we've been talking about vaporization. Vaporization today. You learned about evaporation. They kind of seem the same, but they're actually different. Now, vaporization, it's actually a spontaneous process which occurs at the surface of the liquid. So water to steam, that steam coming off, that's vaporization because it's happening at the surface of the liquid. And once vaporization process starts, it leads into the evaporation, which is a phase change. So where liquid phase changes to a gas phase completely at the boiling point. So like drying the sidewalk in the summer after it rains. Okay. And that's it. Thanks, guys.